Welcome, everyone. Today, we're looking at what is absolutely one of the most powerful tools in all of organic chemistry, Grignard reactions. If you think about chemical synthesis kind of like building a house, most reactions are just like painting the walls or changing the locks. But Grignard reactions, they're your molecular architects. They literally allow you to pour a completely new concrete foundation by creating brand new carbon-to-carbon bonds. Whether you're studying for your Cambridge or Edexcel A-level chemistry exams, or you're just fascinated by molecular construction, mastering this is going to unlock a massive portion of organic synthesis for you. Okay, let's dive into this.
Here's our roadmap for this explainer. First, we'll meet the Grignard reagent. Second, preparation and those super strict conditions. Third, reactions, where we're actually building bigger molecules. Fourth, the step-by-step mechanism. And fifth, some crucial exam tips and common mistakes. All right, section 1. Let's meet the Grignard reagent.
So the general formula for a Grignard reagent is R-MgX. This is what we call an organomagnesium compound. The R just stands for an alkyl or aryl group. Basically, that's your carbon chain or ring. The Mg is, of course, magnesium, and the X is a halogen, specifically chlorine, bromine, or iodine. So a classic example you're going to see all the time is CH3MgBr, which is known as methyl magnesium bromide. Like I mentioned a second ago, these are heavily relied upon in organic chemistry for one massive reason. They form new carbon-carbon bonds, seamlessly snapping two separate carbon structures together.
Now, what's really interesting about this slide is the totally unique dynamic between the carbon and the magnesium atom. In most organic molecules, carbon is bonded to something way more electronegative, like oxygen or a halogen, right? Making the carbon slightly positive or electrophilic. But here, we have a total role reversal. Because magnesium is actually less electronegative than carbon, the bond polarizes the other way. So we end up with a partially negative carbon attached to a partially positive magnesium. This means the carbon atom basically behaves like a carbanion, a carbon with a negative charge. It gets these incredible molecular superpowers, transforming into both a very strong nucleophile and a really strong base.
Moving right along to section 2, preparation and strict conditions.
When you study this preparation, there's one word that's going to flash in neon lights in your textbook: DRY. Dry glassware, dry solvent, absolutely no atmospheric moisture. So I have to ask you, why must absolutely everything be dry? I mean, why is water such a big deal here?
Well, it's because water is the ultimate kryptonite to our Grignard reagent. See, our goal is to react our Grignard with a carbonyl compound to build a really complex molecule. But because it is such an insanely strong base, it reacts immediately and violently with even the tiniest drop of water. If you have methyl magnesium bromide, CH3MgBr, and it touches water, it simply grabs a hydrogen atom. Just like that, your beautiful, complex, expensive reagent is instantly destroyed, leaving you with methane gas and a magnesium hydroxyhalide byproduct. Methane. You wanted to build a complex architectural masterpiece, and instead, you just made swamp gas. That is exactly why your apparatus must be bone dry. To achieve this perfectly dry environment, we use a very specific solvent: dry ether, specifically diethyl ether. But look, the ether isn't just some neutral bystander here. It actually plays a bunch of active roles in making this whole reaction work. First up, it easily dissolves the Grignard reagent as it forms from the haloalkane and magnesium metal. Second, the ether molecules actually coordinate with and stabilize that highly reactive magnesium atom. Third, that stabilization prevents the whole reaction from decomposing. And most importantly, using dry ether means it has been rigorously distilled to contain absolutely zero water.
Okay, let's move to section 3 and see how this builds bigger molecules. If you're taking notes, this table is your master blueprint. It shows you exactly what happens when our Grignard reagent reacts with different types of carbonyl compounds. The pattern recognition here is just beautiful. Check this out. If you start with methanol, which is the simplest aldehyde, you will always build a primary alcohol. If you use literally any other longer chain aldehyde, you're going to yield a secondary alcohol. If you react it with a ketone, you build a tertiary alcohol. And finally, if you react your Grignard reagent with carbon dioxide, you produce a carboxylic acid. Seriously, memorize this table, and you'll be able to predict the outcome of almost any A-level Grignard synthesis question. Let's look a bit closer at that last reaction from our table because it is one of the absolute most important synthetic methods you'll ever learn. When you take a Grignard reagent, let's say CH3MgBr, and react it with carbon dioxide, you are doing something remarkable. You are extending the carbon chain by exactly one carbon atom. The carbon from the CO2 attaches straight to the methyl group, and after we finish up the reaction, we're left with CH3COOH, ethanoic acid. You've literally taken a one-carbon piece and a single CO2 molecule and built a two-carbon chain. It is precise, predictable molecular architecture.
All right, on to section 4, the step-by-step mechanism.
So there are 4 distinct steps in this mechanism. Step 1 is where the magic really happens. Our partially negative carbon, remember that Carbanian superpower we talked about earlier? It acts as a nucleophile and attacks the partially positive carbon of the carbonyl group. This right here is the exact moment that crucial new carbon-carbon bond is formed. Then, in step 2, to make room for this new bond, the carbon-oxygen double bond breaks, pushing the electrons up onto the oxygen atom. This leads us directly into step 3, the formation of an intermediate called an alkoxide ion, where the oxygen now has a negative charge partnered up with our magnesium halide ion. Finally, in step 4, we perform acid hydrolysis to turn that alkoxide ion into our final desired alcohol product.
So, the crucial point is that you cannot just stop after mixing your Grignard and your carbonyl compound. If you do, you're just going to be left with that intermediate alkoxide ion. The reaction requires a deliberate secondary step, adding dilute acid, commonly dilute hydrochloric acid or dilute sulfuric acid. This process is called acid hydrolysis. The whole purpose of this step is to protonate the oxygen, meaning we provide a hydrogen ion, an H+, for that negatively charged oxygen to grab onto. This is the vital final touch that converts the alkoxide ion into the stable alcohol we were trying to build all along.
And that brings us to section 5, exam tips and common mistakes.
Look closely at this checklist. These are the most common mistakes examiners report year after year, so let's get them locked in. First, never suggest using a wet apparatus or an aqueous solvent. Remember, water totally destroys the reagent. Second, always specify dry ether when you're asked for the preparation conditions. Third, when writing out a full reaction pathway, do not forget to write in the acid hydrolysis step. Without it, your reaction literally isn't finished. Fourth, double-check your alcohol classification. Ensure you've correctly mapped methanol to primary, aldehydes to secondary, and ketones to tertiary. And finally, the biggest pitfall of them all. When you draw your final product, please count your carbons. Don't forget that a new carbon atom has been added from the carbonyl compound. If you started with a 2-carbon Grignard and methanol, your product absolutely must have 3 carbons.
We're going to wrap up today's explainer with a bit of a challenge for you to test out your new synthesis skills. You now know that reacting a Grignard reagent with carbon dioxide extends your carbon chain by exactly 1. But what if you were looking at an exam question that asked you to synthesize a molecule by extending the carbon chain by exactly 3 carbons? Based on the carbonyl table we looked at today, what starting materials could you actually choose to make that happen? Think about the sizes of the Grignards and the carbonyls you could piece together. Thank you so much for joining me today. Keep practicing those reaction mechanisms. Keep that glassware totally dry, and I'll see you in the next explainer.